In this example 5, we got the distance formula. Well, now let's have 4 satellites in the sky and the receive right here. Get the signal from the satellites. And the timestamp the receiver got help it to measure the distance, which is given in such a formula. Let me give you the meaning of a notation. This X, put a little hat on the top. That little hat is just to tell you it's an estimate. K is the t equal k at the time k step. Well, the X in the space, you have 3 components: east, north, upward, right? That's why you have the X, Y, Z. So the position here, we use the vector of this xk hat. And then you use the same formula for the satellite 1, put it here, satellite 2, satellite 3, satellite 4. So this little I on the top is not a derivative, it's not a power, just to tell you the I satellites. If I equal 1 means the first satellite, I equal 4 means the last satellites. Right. Well, each satellite also have X, Y, Z. Put the S just to tell you it's the satellites. So it got complicated enough, right? But you can see it. So what's the distance between the first satellite to the receiver? Then if we put 1 here, that's the X of the receiver minus the X of the satellite square plus Y of the receiver minus Y satellite position and Z minus Z. Okay, that's exactly what I'm talking about this. You can simply write it this way if you want. If I don't have this many satellites. Well, what the ABC? It's the known position of a satellite. The satellite position is always known at any moment. So it's a constant. X, Y, Z is the receiver, the user's position. You don't know. But of course, you know, that's not linear. We call it nonlinear. How do we get it linearized? Well, you know how to take a derivative. This looks really complicated, but the math model, again, don't be scared. That's just the noise. Because the real distance, you never know. But the predicted distance is that formula. Depends on your position, you predict it. And the satellite position is known. So this is the measured distance. And this is the predicted distance. Why is predicted? Because the X hat, Y hat, Z hat is the predicted position. You don't know really where you are. Then that's the error. Well, now how do we get the Jacobian? I equal 1, 2, 3, 4. You have 4 of those functions. Then you're going to have a vector function with 3 variables, X, Y, Z, and 4 components of Z1, Z2, Z3, Z4 stand for the 4 distance to the 4 satellites, right? Get it? So that's the complication. But thanks for the good thing, they're all the same because the symmetry in the math. Now the derivative look terrible. Let me do it here at another page. The distance, to make it easier, use what you learned in the calculus 1. That's a baby problem. And then you take this distance to x. You know how to do that, right? You let the r equals x minus a squared, or y minus b squared, plus z minus c squared. And it's r to the 1/2 dr delta r delta x. That's the chain rule. And that derivative is 1/2 r to the 1/2 minus 1 delta r delta x is going to be 2x minus a. And then the other one is going to be square root of r. And to put it back, that's the r. And then this is x minus a. That's the derivative to x. Now you learn this if you take calculus 3 or mathematics method in physical science. Well, do the same thing. Delta d delta y, what is it? Then you change this to y minus b, you get the same thing on the bottom. That's the r. And the delta d delta z, you just change the numerator into z minus c, you get the same thing on the bottom. So you got the idea. That's how you get this complicated thing. Okay, so delta zi k, doesn't matter, that's the time. Take a derivative to x equals x, that's the user, that's the satellite, that's the distance. So how many of those you have? 12, right? 3, 4. You have 2x, 2y, 2z, make it 3, and the satellite 1, 2, 3, 4, and then you get 12 of those partial derivatives. We call it Jacobian. You remember Jacobian. And what is the change? The first row talk about the distance to the satellite 1, that's all 1 on the top. Second row is the distance to the satellite 2, satellite 3, satellite 4, and then to x, to y, to z, you see this is going to be a 4 by 3 matrix. You get a 12, but the things for the symmetry, they're all the same, right? Not that bad. As long as you understand this, everything is the same. Well, that matrix is very, very interesting. Let me add another line. Look here. This, let me draw another one line, it's better because it's too complicated. Let me see my time. Well, I have time. I would rather spend a little more time here. This is the satellite. This is the receiver. The satellite position is SY, and the SZI. And the user is XK. No, we still have a K here. That's the complication. YK and the ZK. So look at this vector from the satellite to the user. That vector is xk minus sxki and the yk minus syik and the zk minus szki. That's very clear, right? Now, the distance is r equals this. Square root, this is square, square, and the square, you write it down here. I call it ri. Okay, that's the same. So if the vector divided by its own length, what you get? When the vector a divided by its own length, what you get? We call it a unity vector, right? And in the very beginning, when we talk about transformation, we talked this. This is a unity vector point from the satellite towards the user. That we call it direction cosine vector, or say unity direction vector. In the same way, like a coordinate, like this I is a unity vector, J is a unity vector, K is a unity vector. The same thing, direction vector. And if you have another one here, your A, and divided by its own length, and this Y is called the cosine. It's really the angle to the cosine to the I, the cosine to the J, the cosine to the K. That vector uniquely determined the direction of the user from the satellite. So now let's look back to this again. See, this first row is exactly the cosine vector from the satellite 1 to the user. And the second one line is the exact direction from the satellite to the user. The third satellite to the user. The fourth satellite to the user. Well, that's very characterized of the user position, because the satellite position is known. Only the user position do not know. But just get this matrix if it's correct. You get the direction from point towards the user. So basically, you get the vector, they give you this kind of thing. You can probably guess where is the user, right? So I add another one tomorrow, next lesson. I'm going to talk about this one. It is related with the time drift. So put another column. Then we got the 4x4 matrix. That matrix in the GPS, we call it a geometric matrix of the satellites. From the user point of view, this matrix completely tell you where are the 4 satellites in the sky. Now, let's assume the user is right here. This go to the first, go to the second, go to the third, go to the fourth. And this matrix, so it's called the geometric matrix of a satellite. When GPS do the calculation, oh, what is that? That's the age of your model here. Let me show you. We still need the linear model. Now, that's your F. Even you have, that's your H here. Even such a bad nonlinear equation, but once I get the Jacobian matrix, not only I got it linear, but it's very meaningful. Tell you exactly from the user to the satellite. The cosine matrix. You remember when we talked about rotation? Talk about the 3 different coordinates, the local coordinate, and the Earth's center, the Earth's fixed coordinate, and also the inertial frame system. We all use this rotation cosine matrix, right? That's it.